Jenkins' fast work and flair for publicity put him out ahead of the pack very quickly. In a 1927 publicity coup, Jenkins unveiled the first long-distance television transmission in history.
It's pretty easy once you have TV on the market, which was delayed by World War II, because TV was ready to be marketed just ahead of World War II, and they had to wait. And that if you could put that in the air and figure out a way to use it, you could see what you were tracking.
And now, television on target. The promise of television reaching into the living rooms of average American families was put on hold by the Second World War, which also served as impetus to advance the state of TV technology in the manic pursuit of new entries in the secret weapon race. Television promised precision and distance, increasingly essential aspects of an increasingly airborne conflict. An autonomous weapon could keep the pilot clear of enemy defenses. An accurate autonomous weapon could pinpoint a power plant and spare the neighborhood around it. That early TV technology was applied to glide bombs, small drone aircraft, and worn-out bombers packed with explosives. Weary Willy B-17s and TDR assault drones saw little combat, but proved prophetic once the technology caught up. Following the war, China Lake continued investigating almost every potential guidance technology imaginable: radio and radar, visible light, infrared, active and semi-active and passive, command-guided and fully autonomous. China Lake experimented with scores of schemes to put rockets and bombs and torpedoes on target, creating increasingly sophisticated evolutions of the rocket sights of the 1940s, and at the same time putting its fire control tech into the rockets. And in an era in which electro-optical technology, TV, was at the cutting edge, the station was already working toward the application of its promise of precision to new generations of weapon and aircraft systems. From television-centered experimental fire control and bomb directing hardware came the ideas for an automatic tracking television guidance system. Such a device had been demonstrated in 1953 at NOL Corona, but the technology of the day still didn't well support the dream. By the late 50s, though, a group at China Lake had begun demonstrating the technology and hardware for what would become the first successful autonomous electro-optical guided weapon, Walleye. Walleye demonstrated just how accurate the TV camera could be. And the weapon's combat op-eval successes became legendary. Larger, longer range, and data link versions followed quickly in the original Walleye's wake. And a powered version, Condor, was developed with industry for even longer range capability. In the opposite direction, China Lake designed a tiny TV missile, the Snipe, to give helicopters and light aircraft an unprecedented precision attack capability. The China Lake team also continued fusing TV technologies into fire control systems, such as ARBs for Skyhawks and Harriers, and early automated weapon targeting systems. The station ran the technology out to the ranges, too, with both in-house innovation and off-the-shelf application for data collection and drop scoring and event control. The station put TV into sophisticated remotes to support T&E and simulation as targets and as test platforms. And China Lake presented full-on fighters to its developmental missiles. China Lake's instrumentation efforts also resulted in the creation of the shuttered video technology that would become industry standard. Station efforts to advance walleye and condor and TV guidance in general resulted in smaller, even more precise electro-optical devices. Triple LTV that allowed missiles and sensors to function in extremely low light. Odd spectrum imagers combining technologies to provide clear vision in the dark. Seekers that could penetrate fog and haze and dust. And many of today's lumbering giants of the battlespace, weapons little evolved from the convertibombs that tried to displace walleye in its early days, owe much of their seeker and data link technology to those China Lake efforts, as do the guidance systems for harpoons that turn them into slams, and the radical CCD imagers for air-to-air missiles. And a new generation of imaging technologies has spawned a new generation of weapons. Tiny, elegantly simple, and unerringly accurate, whether fired from ship or shoulder, helo or Hummer, rubber boat or toy plane. The little spike is a new kind of weapon for a new kind of war. The pursuit of precision continues, with the electro-optically eyed descendants of Weary Willie and Walleye wearing imaging seekers that are as far from the TV guidance packages of the 1960s as those were from the mechanical TV scanners of the 1920s. Compact, computer-packed automatons with seekers that can see through haze and darkness to pinpoint targets from the air and from the shoulder, with the ubiquitous offspring of the data link pods controlling nearly everything in the battlespace arena. But that's another story.
Bombing a well-defended tactical target has always been a difficult mission. Anti-aircraft fire harasses the bomber in the target area to reduce his accuracy well below scores achieved during training missions. Operational commanders, therefore, must send out more ordnance to knock out a specific target, but they are hampered by not having enough aircraft to cover all significant targets in any one combat area. One answer to this compound problem is Walleye, a glide bomb developed by the Naval Ordnance Test Station. This revolutionary weapon is guided by a self-contained automatic tracking television system, which frees the pilot of further control responsibility after launch and allows him to escape or attack other targets. Walleye's guidance system emits no signal, thus it cannot be jammed by electromagnetic radiation. At launch ranges of 16 miles, as long as the guidance system remains locked on the target, Walleye will maintain a CEP of less than 15 feet. The 1,100-pound walleye is 11 feet 4 inches long, 15 inches in diameter, and has a 45-inch wingspan. The weapon consists of 3 basic sections or subsystems: guidance, warhead, and control. Over 80% of the total weapon weight is warhead. The high payload-to-weight ratio is a benefit derived from the absence of a propulsion unit. The Walleye guidance system combines a gyro-stabilized television camera with a passive, automatic tracking system. The sensing element is the camera, consisting of a lens and a Vidicon tube mounted coaxially with a gyro. The assembly is supported by a gimbal system which allows the camera to move through an angle of 30 degrees in any direction. After launch, Walleye takes a glide path instead of a short ballistic trajectory. Under nominal launch conditions of Mach 0.9 and a 35,000-foot altitude, Walleye can attain a maximum range of 16 nautical miles with a glide ratio of 3:1. Launched as low as 200 feet off the deck, the weapon can glide for 4 nautical miles. The warhead, developed expressly for walleye, is a linear-shaped charge with a star-form cross-section. The charge, encased in a steel jacket, exerts more destructive force than a conventional 1,000-pound bomb. First, 8 tight beams of high-velocity steel fragments rip through the target at more than 11,000 feet per second, followed by the blast of a high-pressure shock wave. Test warheads have torn through 4-inch steel at distances of 20 feet and have shattered reinforced concrete 4 feet thick. Walleye en route and launch procedures are quickly learned. Prior to every mission, the pilot will, of course, run through the walleye ground checkout. Arriving in the target area, he switches on master arm and begins the attack. He acquires the target in his gun sight, shifts to the display, and maneuvers to put the target in the crosshairs. As he does this, he presses and holds the trigger switch to uncage the gyro and watches for the abrupt, unmistakable lock-on. Holding the trigger, he presses the bomb release. Display and ready light black out as walleye drops away. The pilot now is free to escape or attack other targets. Within the weapon, automatic tracking assumes control. The camera continues to feed video information to the tracker, which generates control signals steering the weapon toward the target. As the target image expands, Walleye's seeker tracks newly resolving details until the moment of impact. The Walleye weapon system is expected to furnish the operational commander with a positive means of accomplishing his close air support and interdiction missions, with available aircraft, with reduced expenditure of ordnance, and with the expectancy of reduced aircraft losses. Walleye is scheduled for operational release to the fleet in 1966. As the A-7 launch aircraft heads away from the weapon launch point, Walleye continues on course. Guided either by autopilot or from a distant control aircraft, Walleye glides toward the target, the Ninh Binh Bridge. Last-minute course corrections guide Walleye to the exact target point. One 2,000-pound warhead, guided in with pinpoint accuracy, did what hundreds of iron bombs had been unable to do. Walleye is not a new name to the fleet. Development of Walleye began in the late 50s, and Walleye 1, a contrast-guided weapon, was introduced to the fleet in 1967. Development of Walleye 2 with a 2,000-pound warhead started in 1968. Then in 1970, the development of an extended range version of Walleye 2 began at NWC China Lake. Now we have Walleye 2 Extended Range Data Link, a glide weapon with a 30-mile range. This member of the walleye family can be controlled by the pilot through a long-range video RF data link with the weapon after launch. The pilot sees the general target area on a high-resolution video display, and when he's within the weapon launch parameters, he releases the walleye. Since walleye is a glide weapon, it leaves no contrail, and it has minimal radar reflectance. After launch, the walleye will auto-track to the target, or it can be controlled by a pilot in another aircraft equipped with the data link pod. After release, the launching aircraft could leave the area. Walleye can also be launched and controlled from the same aircraft. As walleye glides toward the target, the command pilot, via the data link, may update the weapon's aim point as prominent features of the target become visible. As walleye nears terminal impact, the pilot can update the lock-on point until he finds the specific part of the target he wants. He may hand track or allow the weapon to auto-track until impact. This was a totally inert weapon. On May 9, 1973, an all-up walleye with a live warhead was loaded at China Lake for a launch over the Pacific Missile Range. Loading takes from 10 to 15 minutes, including checkout, and the weapon can be safely brought home to a carrier if the mission aborts. The launch aircraft acquired the target at 10 miles and the walleye locked on. The walleye was launched on a flight to demonstrate the missile's level launch, low altitude, long standoff capability. The target was a harbor utility ship underway at 10 knots on the Pacific Missile Range. As planned, walleye hit the ship at the base of the superstructure. The ship was totally destroyed. Between January and July 1973, walleye hit within its CEP on all 10 launches. 9 of those were direct hits. Walleye 2 Extended Range Data Link is now the only system of its kind which has been combat proven.
Condor is a television-linked air-to-surface standoff weapon system. Condor was developed by North American Rockwell under technical direction of the Naval Weapons Center. From a maximum launch altitude of 40,000 feet, the Condor missile can reach target 55 miles away in about 6 minutes. After launch, the aircraft is free to depart. When the missile glides to its programmed cruise altitude, it fires its motor and follows a programmed route to the target area. A two-way data link enables remote surveillance of the missile path and lock-on from the aircraft. Homing is automatic. Missile guidance contains a TV camera with lenses for wide or narrow fields of view, a walleye-type contrast seeker, and an autopilot. On arrival at the launch point, the computer launches the missile. The data link switches to RF. The pod's mission recorder camera starts filming the picture transmitted to its receiver. On gliding to programmed cruise level, the missile fires its motor. On acquiring the target area, the bombardier switches to the narrow field of view. When he identifies the target, he presses the missile follow button to cancel the flight program, slews the camera to put the target in the gated area, and releases the button to lock the seeker. The black square disappears at lock-on. At this point, the missile may be more than 80 miles from the launch aircraft. The bombardier may retarget at will by pressing the button, slewing to the new aim point, and releasing the button again. Or he may hold the button and fly the missile into the target. Condor Fleet evaluation is scheduled for 1972.
A major problem in modern warfare concerns stationary or slow-moving combat vehicles. How can they fire their weapons accurately, then quickly and safely leave a hazardous area? The snipe weapon is one answer to this question and is currently under development at the Naval Weapons Center, China Lake. Snipe uses a television seeker for automatic target tracking and a rocket motor for zero-velocity launch conditions. Its shape-charge penetration fragmentation warhead is devastating against such targets as tanks, trucks, gun emplacements, and personnel. Snipe's design philosophy permits a vehicle to shoot, then scoot. This was the first purely ballistic ground firing of the weapon, performed in March of 1967, to obtain data on airframe launch characteristics. The standard 2.75 rocket motor is capable of accelerating Snipe to a speed of 550 feet per second from a zero-velocity platform. The eye and brain of the weapon is its TV guidance system. A Vidicon tube is fixed to the airframe. A gyro-stabilized gimbal is located ahead of the tube. The lens is free to rotate about a point equal to its center of focus, thus ensuring a sharp image on the face of the Vidicon. In this lab demonstration, Snipe successfully tracks a simulated tank. In actual usage, the launch vehicle will carry a monitor which will display exactly what Snipe is seeing, as evidenced by these captive flight tests. Snipe uses a new concept for electro-optical tracking. Two horizontally separated contrast points are detected, which keeps the weapon centered on target during closure. This method of tracking allows direct impact on a variety of objects. Snipe's lightweight and compact size permits rapid attachment and multiple carriage. The weapon is prepackaged for simplified combat usage. Connection to the operator's monitor and firing console is made through the aircraft's umbilical. Snipe's advanced guidance and monitoring system allows a series of weapons to be aimed and fired in rapid sequence. There is no need to remain in a hazardous area after weapon launch. This was the first ballistic firing from a helicopter, filmed in slow motion. It was performed to obtain valuable launch transient data. Current tests involve firing Snipe from its proposed launch platform, the Huey helicopter. Extensive experimentation has shown that Snipe will not only reduce helicopter vulnerability, but will be a well-needed addition to the military's store of armaments.
ARBS, Angular Rate Bombing System, an advanced fire control system for light attack aircraft. ARBS is a computer-controlled fire control system which uses a laser and video tracker, tracker electronics, digital computer units, a head-up display, cockpit controls, and a weapon data insert panel. The ARBS accurately puts a variety of ordnance on the target. The nose-mounted dual-mode tracker can automatically track visual or laser-designated targets. The laser designator enables ARBS to track targets and to release weapons automatically, day or night. As the pilot controls the aircraft and the ARBS system, selected cockpit control positions are telemetered, displayed, and recorded in the ARBS acquisition lab. Head-up display imagery, the same as appears in the aircraft, is displayed in real time in the acquisition lab. Video imagery from the aircraft's video tracker is displayed on a television monitor. A second function of the ARBS lab is the recreation and simulation of ARBS flights for detailed analysis. An ARBS system in the simulation lab is exercised as if it were flying. Flight parameters are fed to the system by a systems engineer acting as the pilot. Software can be developed and perfected on the ground rather than by trial and error flight testing. With the system components tested and the software package updated and debugged, the ARBS is ready for additional range tests. Tests which consistently put the ordnance on the target.
Engineers at the Naval Weapons Center, China Lake, California, are developing a head-coupled television system with a number of potential applications. The experimental system is a closed-circuit television chain that uses the natural movements of the observer's head to pan, tilt, and roll a remote television camera. The observer views, through a pair of oculars, the image displayed on a miniature picture tube. The picture tube and camera Vidicon have a 1,000 line resolution. In these tests, the camera is mounted outside the laboratory and the operator is located inside. The operator, by the simple, natural act of looking in the direction he wishes, can view any portion of the remote camera surroundings. Regardless where the operator is located with respect to the camera, he has the visual sensation of being at the camera's location. At the same time, his hands are free to perform other functions that may be required. Provided with remote control manipulators, he would be able to perform many tasks in situations where remote surveillance and the ability to work at a safe distance is desirable. One of the prime objectives of the program is to explore the feasibility of using head-coupled television aboard ships to acquire, track, and designate targets directly to radars or indirectly through fire control computers. Optical tracking systems are particularly useful in instances where targets are difficult for radar to acquire, such as shore targets or low-flying aircraft and surface vessels. The head-coupled TV system bypasses many of the limitations of present optical trackers. When using current tracking systems, an operator must translate what he sees through his brain to his hands, arms, and legs in order to keep the optical tracker on the target. The task requires a high degree of physical coordination in manipulating the director while compensating for ship's motion. The head-coupled system would use the natural movements of the operator's head to generate tracking signal input to a fire control computer. A test program explored the human factors potential of the system in detail. Subjects chosen for the test were in turn strapped in a ship's motion simulator capable of approximating various sea states. Each subject was required to try to keep the display crosshairs centered on the target indicated by the test conductor. Analysis of the accumulated data revealed that head coupling not only resulted in a high degree of tracking accuracy, but also demonstrated the ease with which the operator could perform his tracking function. Exploring other possible applications of the system, engineers conducted a series of experiments aboard a helicopter. Test equipment, video recorder, and camera were secured to the cabin floor, converting the craft into a flight laboratory. Engineers in the cabin, acting as trackers, were able to locate and track both stationary and moving targets even while the helicopter was flown through various maneuvers. The head-coupled TV system is a human factors approach to tracking and remote surveillance that ties man and machine together. Visual, mental, and physical processes are translated into electrical signals via the shortest and simplest route, the natural movements of the operator's head. This program is an example of exploratory development at the Naval Weapons Center, with the potential of broad industrial and military applications.
It has long been recognized that final evaluation of the effectiveness of a homing missile requires knowledge of the missile's performance in a multiple target environment. To achieve full effectiveness, the missile must be able to select and acquire proper targets when they appear in various target formations and separations. Conversely, studies also indicate that properly spaced multiple targets can provide an effective countermeasure against certain missile guidance systems. Therefore, development of a satisfactory method of flying multiple drone targets in controllable formations assumes increasing importance if improvement is to continue in both offensive and defensive capabilities of air warfare. However, until recently, attempts to provide effective flight and control of drones in formation have been unsatisfactory. At the Naval Ordnance Test Station, A method has been evolved for presenting two target drones in well-controlled formation flight. This Knott's method of dual drone formation control is based on the employment of a television camera system and data link. These are integrated with the standard drone control tools of radar, telemetry, and radio. The essence of the method is flight control of the second drone through visual observation transmitted to ground control by the television camera carried in the lead drone. The mirror in the forward section is mounted at a 45-degree angle to the flight path. This permits the forward-pointing camera a side field of view. The mirror mount is motorized and can, by remote control, provide a variation of 60 degrees in the horizontal plane and 40 degrees in the vertical plane. This capability facilitates acquisition of the second or slave drone. In the camera section, the remotely controlled zoom lens can provide a field of view varying from 4.8 to 48 degrees. The TV drone, tail painted green for easy identification by control aircraft, carries a dummy balancing pod under the wing opposite the TV pod. The slave drone carries two dummy pods so as to present a uniform radar profile for the missile control system. First launched is the slave drone. Takeoff is standard NOLO procedure. A T-28 aircraft takes over the airborne drone. The T-28 delivers the slave target to its control aircraft, which has been orbiting a rendezvous point. The TV drone is launched. The standard Knott's test course for formation drone control is an oval racetrack pattern. Minus 30 seconds. The missile ground control plots the two drone formation and prepares to fire. Smoke is keyed on each drone. The drones, under complete remote control, fly straight and level. Missile is launched. In the event of an aborted test, control aircraft once more take over the drones and resume the test pattern. After all presentations of the target are completed, the target aircraft are flown back for standard NOLO landing recovery. This Knott's-developed TV manual control system for presentation of dual targets has provided a satisfactory solution for initial formation target test requirements. Testing thus far has been largely successful, and both ground-to-air and air-to-air intercepts have been accomplished with this interim system.
On March 30th, 1973, the first successful flight of the QF-86H occurred at the Naval Weapons Center, China Lake. The QF-86H is a real-size, all-attitude, highly maneuverable, remotely piloted vehicle. It will be used to test air-to-air weapon systems in a realistic air combat maneuvering environment. The aircraft will retain man rating. The target system consists of the QF-86H aircraft, a ground control station, and an MSQ-51 radar van. A standard television camera provides the remote pilot with a 45-degree forward field of view. The remote control pilot flies the aircraft from an actual F-86H cockpit located in the ground control station. A TV monitor and XY plot provide the pilot with vehicle position and attitude.
Rotation occurred at approximately 110 knots. Liftoff at 125 knots. Here's the takeoff as the remote pilot sees it. The flaps and gear were intentionally left down, and 155 knots airspeed was maintained around the pattern. The runway was seen from approximately 10 miles out. The remote pilot flared the aircraft normally just prior to touchdown. The aircraft made a 100-degree turn onto the non-duty runway. This 10-minute flight on March 30th, 1973 was the first successful flight of the QF-86H, an air combat maneuvering all-attitude target system. It could be the harbinger of realistic weapon systems test and evaluation.
Targets. All shapes, all sizes. Targets to test the effectiveness of prototype weapon systems. Targets which realistically simulate enemy installations. Targets which simulate the known operational characteristics of enemy combat aircraft. Full-scale targets like these offer accurate infrared signatures and realistic radar reflectance. They can recreate documented and estimated combat maneuvers. The Navy's newest air target is the cost-effective QT-38A. Using surplus Air Force T-38A airframes, NWC, with contractor support and under the Naval Air System Command sponsorship, is building a series of cost-effective, remotely piloted, full-scale targets. When the setup pilot leaves the aircraft, following the pre-flight checks and engine run-up, the remote pilot in the control station literally becomes the pilot of the airplane. The ground crew completes the final checkout and arms the safety destruct system. As the remote pilot moves the controls in his facsimile cockpit, the aircraft responds as if the aircraft were manned. The remote pilot launches the aircraft basing his judgment on the nose-mounted TV camera with its 45-degree field of view. This one pilot controls the takeoff, the target presentation, and the landing. No handoffs are needed. There is no control aircraft.
As the shooter closes on the target, the scenario is monitored optically and electronically by range instrumentation. If the first missile doesn't destroy the target, additional presentations can be made on the same flight. For safety reasons, targets knocked out of control are destroyed by the flight termination system. If the shooter aborts the mission or the weapon doesn't seriously damage the target, the QT-38A is brought home. Again, the remote pilot has complete control of the aircraft as he brings it in, using the television monitor as his guide. The QT-38A is reliable. The cost is less than subscale targets. Performance realistically simulates enemy aircraft. The system is available now.
Volkswagen chassis, a 65 horsepower engine, a 3-kilowatt generator, and a TV camera. The nuts and bolts of the Naval Weapons Center's remote-controlled dune buggy. dune buggy is a drone vehicle able to simulate maneuvering sea targets. It can maintain a constant or variable velocity. It can make smooth, continuous turns and is also capable of zigzag maneuvering. Maximum speed is 60 miles per hour. The remote controller steers the vehicle from within a mobile control van. A TV camera mounted on the vehicle provides the controller with a 5-degree forward field of view. The speedometer and throttle indicator display vehicle velocity and position. The dune buggy is visible to the eye from a slant range of approximately 15,000 feet. It can be augmented for visibility on an airborne radar. The time position tracking system developed at NWC enables vectors to be derived between the moving target, the aircraft, and the weapon impact. Data accuracy is within 10 feet. The system consists of azimuth encoders and TV cameras for target tracking, a radar station for aircraft tracking, a data computation room, and a data reduction room. Located on 2 cine-sextant tracking camera mounts, spaced 1 1/2 miles apart, the azimuth encoders and TV cameras provide continuous plotting of target motion and weapon impact. The digital encoder data is inserted on the TV video at each camera site. The images are then combined with range time and microwaved to the data computation room. Here, the images are displayed and recorded in a single video format. Aircraft tracking is done by a ground radar station. Range, bearing, velocity, and release point are plotted for analysis in the data reduction room. In approximately 24 hours, data can be reduced with an accuracy of 10 feet. A calculator rotates and parallaxes data monitored from the TV video and correlates it with data produced by the radar. The end result is a continuous plot of vehicle motion synchronized with aircraft flight path, weapon delivery, and impact. The remote-controlled dune buggy is the first land-based drone vehicle to adequately simulate maneuvering sea targets. It is a low-cost, lightweight target with high performance and reliability. Together with the time-position tracking system, the dune buggy requires no setup time between aircraft passes. As many as 24 passes can be made in a 1-hour period. Dune Buggy 73, NWC's newest contribution to drone technology.